Good morning or afternoon. I want to use this video to go over question 4 from 2017, which when I looked it up, I realized this was a question that in that particular year not only drove my students crazy, but it also caused a million memes written about potatoes everywhere. This year in 2017, they had a thing about food. There was a question about potatoes and there was a question about bananas, and neither one was a favorite of students. So I want to go through it. It's actually a question that comes from chapter 6. So if you're trying to organize, this was a question that's a differential equation question. There are parts to it that I think are easier than what you might realize. And there's also parts of it that have little details that I think are easy to leave out. So we're going to go through that. I have my answer that's going to be on the screen. And I also have the rubric that you can see how the points were awarded. So here's what's happening. We have a boiled potato, and initially the temperature at 0 when it's taken out of the boiling water is 91 degrees Celsius, and then obviously it's cooling off. The temperature never goes below 27. It's always greater than 27 for all the times. And the temperature can be modeled by the differential equation, that dH dt. And so what that basically is in terms of T is time and H is the temperature of the potato. And then finally, they tell us that, again, that H of 0 is 91. So at time 91, time 0, the potato is 91 degrees. So part A wants you to write an equation for the tangent line. So if you think about tangent line equations, you need a point, which you have because you have the 0 for T and the 91 for H, and then you need a slope. And the slope's going to come from the dH dt because that's your derivative equation. Now, the key here is this derivative equation is only in terms of h's right now. So the only number you can plug in is the h value, which is 91. That's that temperature. So if you go down to my work, here's kind of where I started. I wrote down my time is 0, h is 91. My derivative equation, I'm going to put 91 in for h to get a slope. Now, you will have a calculator on the AP test, even if in situations you won't necessarily need it. So use it so you don't have to worry about mental math. So 91 minus 27 is 64, and then you take negative a fourth times it, you get negative 16. So here's my equation, and I did try to write it in terms of h's and t's just to be consistent. So instead of like y minus a value, it's h minus a value. So h minus 91 equals your slope negative 16, and then t minus 0. It wants to write it, they would accept any form. So as long as you have a tangent line equation, you're good. But then it wants to use that tangent line equation to figure out what happens at time 3. So you're going to replace your t with 3. So I did a quick distribution, add 91 to the other side, and then put 3 in. At time 3, it is 43 degrees Celsius. I don't know if you'd have to label the unit, but I think it's a good habit to get into. So their work, just so you can see scoring, kind of the same idea. They actually didn't really take, here's my tangent line. They kind of did it out of order. They did the slope first. So if you got a slope of negative 16, you get a point. Then the second point is writing a tangent line. They did write it as y equals, so you don't have to write it as h equals. They're pretty flexible. As long as it's any form that's similar to that's equivalent, you get a point. And then your last point, if you got 43 degrees, again, you could show a lot of work or a little work. As long as you get 43, you get a third point. So 3 points just from part A, which is good because part A is probably the easiest. Part B wants you to use the second derivative to determine if your answer that you just got is an overestimate or an underestimate. So if you think about your second derivative is going to tell you about concavity. So you're going to know, is it concave up or is it concave down? And if you know which one it is, you can determine an overestimate or underestimate. So here's where you have to take a derivative implicitly twice, which is not something we do a lot. This would have been done in the very end of chapter 2 is when this part happened. So your second derivative is deriving your first derivative. So if you look at your first derivative, which was right here, the h dt, when I take the second derivative, I'm still going to have the negative 1/4. The derivative of h is again dh dt because it's the derivative in terms of time. The derivative of the minus 27 is 0. It's gone. So when I wrote my second derivative, I just wrote the negative 1/4 and then the dh dt. Now you have to replace that because you know what dH dt is. Anytime you derive something twice implicitly, you're going to replace your first derivative with what the first derivative was. So you'll notice right below that I wrote the first derivative again. A negative a fourth and a negative a fourth is going to give me positive 1/16, and then I still have h minus 27. Well, the one thing I know about the temperature, which is h, is it's always bigger than 27, which means no matter what I plug in here, I'm always going to get a positive value. I'm going to get 1/16 times something positive. So that's always greater than 0. I use that to draw a picture. So if it's always greater than 0, that means it's concave up. So I drew this little kind of half U shape here. If it's concave up and I draw a tangent line, that's what they're not going to grade my picture, but it helped me. Anytime I have something concave up, a tangent line is always going to be under the actual function because of that concavity. So what that means is it's an underestimate. So here's what I wrote. We know h of t is concave up. You could explain that a little bit more, just the second derivative is greater than 0. So that means it's an underestimate in part A. And what they did, I think they did actually very similar. Yeah, they didn't give many, they only gave 1 point for this. In my mind, I feel like it should have been worth more than that. They took the second derivative just like I did. They showed that you always get something bigger than 0. So that means it's concave up. It's an underestimate. In my opinion, a whole lot of work for 1 point. Then part C, which is the tough part. So part C, now we have this new equation that we're going to use to model the temperature of the potatoes. So we're not using H anymore. That doesn't get used at all in part C. We're using this G equation, which is also a first derivative implicit. And it also has the same initial condition, 0 and 91. And it wants to use that to come up with an expression for your original function, which means you're going to have to integrate, and then use that to make an approximation. So to integrate this, and this is where I know students had a huge issue with this one, because when they went to integrate, what they didn't realize is you actually have to separate it. Because the way this is written, dg dt, what that means is everything over here should be in terms of t's. It's not. It's in terms of g's. So the best way to think of it is if it said dy dx. In order to integrate it, everything would have to be in terms of x. It's not. So this means it is something you have to separate. And that's where this really comes into more of a chapter 6 type question. You need to get the g's on one side with the dg and the t's on the other side with the dt. And you might be looking and saying, well, there aren't any t's. You're right. So the dt is going to be kind of by itself. So here's my work for that. So here is my original equation. I moved all of this in parentheses to the other side by dividing it. I actually didn't move the negative sign. I kind of felt like I don't want to make this worse than it is. So I left the negative where it is. And the only thing on that side is just the dt. So I multiply by dt on the other side. Now, this is an integral that is a little more work than normal. You're going to have to do a real quick u sub, although it is one that doesn't have an adjustment. Your u is going to be g minus 27. The derivative of that is just dg, so no adjustment. I made a little note there. This means that this is a u to the negative 2/3 because it's in the bottom being taken to the 2/3 power. So power 1 greater divided by that power. So power 1 greater would be to 1/3 power divided by 1/3 is the same as multiplied by 3. So here's my integration. On the other side, I didn't really do much with it until over here. The integral of like a -1 is a negative t plus c. Don't forget your plus c. At that point, I decided I want to find C, and I used my initial condition. My initial condition is G is 91 when T is 0. So I put 91 in here. Again, have a calculator close by. 91 minus 27 is 64. 64 to the 1/3 power is 4 times 3. You get 12. So C is 12. So here is my particular solution. I don't know if you have to get G by itself. They actually never said that you did. I may not have got full credit because I didn't. I was just so excited that I figured out how to get to that point. Finally, the last thing you have to do is use that to figure out what happens at your initial condition, which was what happens when T is 3. So I actually solved this for... I was solving for G and I plugged in 3 for time. So I put the 3 here. So negative 3 plus 12 is 9. I divided both sides by 3 to get rid of that 3 in front. I got 3. To get rid of the 1/3 power, I took it to the 3rd power. So this is 3 cubed, which is 27. So G minus 27 equals 27. I added 27 to both sides. And my final answer, which I crossed my fingers and hoped was the right answer, was 54. Here's how they scored it. And to me, this part was by far the hardest, but it is worth a lot of points. So there's some points you could get without getting it fully correct. So the first step is you have to separate it, which that was the issue. Many students didn't even realize you had to separate it. So they separated it the same way I did. There are options. You could move the negative to the other side and still consider it separated. They only gave 1 point for integrating, which I thought was kind of stingy. In my opinion, they gave too many points for part A and not enough for B and C. So you're integrating again is what I just showed you. You get 1 point for realizing that you should have a plus C and figuring out how to find that C value. So they kind of combine those points. you get 1 point, and it doesn't say that G has to be by itself. It just says as long as you have an equation that involves G and T. So I think I got full credit with mine, even though I didn't make mine nearly as complicated looking as they did. And then your last point is, can you use that to find G of 3? So your G of 3 is what you get when you plug in 3, you get 54. I'm not sure because I never got G of T totally by itself. I'm thinking I might have got 4 out of 5 on that, which for as difficult as this question was, I'm pretty happy about. They have the same notes that we saw in class. If you don't have a plus C, don't involve a plus C, the most you can get is 2 points. If you never separate variables, which was the biggest issue for students, you don't get anything. A thing to realize when you're looking at a derivative equation, let me pull it back up one more time. Anytime you're looking at a derivative equation and trying to figure out if I need to separate it, realize that this bottom value here, this dt, that's telling you what this should be in terms of. If it's not, if this is not in terms of t, then it needs to be separated. Just like if it's a dy dx, if it's not in terms of x, then it needs to be separated. And I think that was the most difficult part of that problem. So that was question 4 from 2017. Definitely a challenging one, but one that you can kind of have near you if you see something like that to reference. See you later, guys.